Hello and welcome back, everybody. Moving on to the last section in chapter 4. I'm calling this section Polar Curves in the Plane. You're probably getting a bit of flashback now to really quite early in the semester when we were studying the complex numbers. I introduced the polar coordinate system at the time for complex numbers, but I did mention how it could be applied to generically two-dimensional space, and that's what we're going to be analyzing today, is really thinking about the xy plane underneath these polar coordinates, and in particular we're going to draw some curves in the xy plane using polar coordinates. So we're going to see what that looks like. So let's think about all the way back to that complex section. What were polar coordinates? Well, they were coordinates which determined uniquely a point in the xy plane dependent on its absolute distance from the origin, which also is known as the radius, or r, as well as an angle from the positive x-axis, which was going to be denoted by theta. And so we used kind of parentheses, and it looks, looks, in quotes maybe here, just like an xy point, but should be interpreted differently, right? We don't interpret the first entry r as an x value or the second entry theta as a y value. They have truly different interpretations. And this is why, if we remember all the way back, I did start to use a subscript POL on those sorts of points, and I will eventually get back into that subscript today. Anyway, let's recall how we plotted some points using the polar coordinate system. This is what the coordinate system kind of looks like. These are our equivalent grids, grid lines in the polar system. Of course, it kind of tells you why it's called polar, because if we look at a globe from above, this would be like the North Pole, and all of our longitude lines would extend out from the North Pole, so it'll be longitudes. And latitude lines, at least near the North Pole, look very much like circles, right? Because they kind of circle the entire globe. But near the North Pole, they just kind of circle the North Pole, so these are latitudes. So that's why we're calling it polar coordinates. And if we think about plotting points, we can recall pretty well from where we were before. Maybe the points I want to plot are 1, pi over 4, 2 pi and pi, and root 3, 3 pi over 2. Then to plot 1 pi over 4, I'm going to go out one radius unit. So that's, you can think about it along the x-axis still, but one kind of unit from the origin, and then I'm going to move up by pi over 4. So the angle of pi over 4. Similarly, if I want to plot the point 2 pi comma pi, I'm going to go out 2 pi along the x-axis, which is about 6.2, somewhere around there. And then I'm going to rotate around the origin by exactly pi, and I end up at my point 2 pi comma pi. And finally, if I want to look at the point root 3, which is about 1.7, and 3 pi over 2, then I jump out maybe 1.7, which is about there, and then go all the way around 3 pi over 2 to end up at my point. So that's how you would plot each of those. And we should recall that we do have these formulas which allow us to transform. Maybe let's recall the xy version was just called Cartesian, so the one we're used to is called Cartesian. Cartesian coordinates, two polar and vice versa. And the formulas we used was, suppose we start with a Cartesian point, we can end up in a polar point, r and theta, by defining r as the square root of x squared plus y squared, and theta ended up being kind of the inverse tangent of y over x. As long as we're in the fourth or first quadrant, it ends up being the inverse tangent of y over x plus pi if we're in the second or third quadrant. And specifically, I guess, when you're looking at, these are when x equals 0, also known as the y-axis. So if you're directly on top of the y-axis, then it turns out it's just the sine of the y value, meaning plus or minus sine of the y value times pi over 2. So that's how you would start with a Cartesian coordinate and end up in a polar coordinate. If you wanted to do the reverse, you could start in a polar coordinate and end up in a Cartesian just by saying, well, x is going to be the radius times cosine, because you think about it, you're moving out by some radius, and then the x value is the cosine of theta on that specific radially scaled unit circle. So it's no longer a unit, it's a radius circle. And y is going to be r times sine theta. So similar, sine theta defines y on the unit circle, but when r is not 1, it's no longer a unit, so you're on some larger circle. So that's how you can find the Cartesian points out of the polar points. Doing a couple examples of moving between these points, let's say that I start with a Cartesian point, negative root 3, 1. Well, let's just plot that as a Cartesian point really quick. So negative root 3 says along the x-axis, I'm going to go out, maybe that's 1, 2, 1, 2, 1, 2, 1, 2. Negative root 3, so negative 1.7 is about out here, and then a positive 1 in the y-axis. So I'm thinking along the lines of that. That's me thinking in terms of Cartesian coordinates, but in terms of polar coordinates, what do we actually want to think is that this point lies on some circle around the origin, and we are going to ask a question of, well, how big is this circle? So what is the radius r, and how far have I moved around the circle? Some amount theta. Okay, so that's how we want to reinterpret the point negative root 3 comma 1. We get there basically by plugging those values in here. So I'm going to replace x squared here with negative root 3 squared and y with 1 squared. That's going to give me the square root of 3 plus 1, square root of 4, also known as 2. So it looks like r is going to be 2. And then if I'm looking at theta, I'm going to replace, well, I need to know which quadrant I'm in, or in particular which x value I have. I have a negative x value here, pretty easy to note. And so I'm going to be looking here for theta. What is the inverse tangent of 1 over negative root 3? Well, that ends up being negative pi over 6 if I were to plug it into my calculator, but of course I see this plus pi here, so I'm going to add pi to that. I'll end up with 5 pi over 6, which makes, when you think about an r being 2 and theta being 5 pi over 6, that makes sense looking at this. That's about 2 and then over 5 pi over 6. You can also do the same thing with the point 1, 1, but I'm not going to go through that here because we actually already did in our earlier discussion of polar coordinates. Let's do one case of transforming maybe a polar point into Cartesian. We're going to take the point root 2 pi over 4. We're going to convert to Cartesian using our formulas here. We're going to replace r with a root 2 and theta with pi over 4, r with root 2, theta with pi over 4. That's going to give me exactly, well, cosine pi over 4 is 1 over root 2, so that's going to give me that x is equal to 1. Sine pi over 4 is 1 over root 2, so that's going to give me that y is also equal to 1. So it turns out that this point, root 2 pi over 4 in polar, happens to be the Cartesian point 1, 1. And actually, if we plot this, it's going to make sense too, right? If I go out maybe root 2 amount here, and then I go up by pi over 4, you're looking right there, that makes sense to be approximately out by 1 in the x direction and 1 in the y direction. You get to the same point. So points are cool and all, but we're in kind of in the section of parametric curves, right? So the question is there a way to have a polar curve? Can we get some sort of curve in the polar plane, right? Some curve that maybe does something like that, like we have with parametric curves, kind of that we could plot in the polar plane. The answer is, of course, yes. So how are we going to do this? Well, we're going to define a polar curve as a function r. So it ends up being that the curve is the radius, but the radius is allowed to depend on theta. Okay, so that's the point of a polar curve, is a curve where the radius depends on theta. And why would that make sense? If I go back to kind of just a generic curve that goes around itself in the plane, you think about it, when theta is 0, that's where I intersect the x-axis. When theta is pi over 4, that's where I am intersecting that line. When theta happens to be pi over 2, I'm there. 3 pi over 4 over there, pi, I'm over here. And at each point along, right, when I'm checking all my theta values, at each point here, the radius, kind of that distance from the origin, depends on how much I've rotated around in the theta direction. So that radius from the origin is going to either grow or shrink depending on how far I've rotated around the origin. So it makes a lot of sense that this is how we're going to go ahead and think about these functions. We'll actually get used to plotting them later, but that's how we should think about it. It's just that a polar curve is going to be the radius as a function of theta. And we're going to plot it using, of course, the polar coordinate system, where we put the function of theta, r, being a radius, in for the radius in the polar coordinate system, as well as we put theta, the independent variable, in for theta in the polar coordinate system. And then we go ahead and plot. So let's actually try to plot one of these. This first one's called the cardioid. And cardioids are kind of these famous polar curves that are known to be heart-shaped. You know, you got this Latin root card, meaning heart, like cardio, cardiology. So it's a heart-shaped curve, and they're defined either symmetrically about the x-axis using some r naught over 2 cosine theta minus 1, or symmetrically about the y-axis using some r naught over 2 sine theta minus 1. In particular, theta is always going to be in the range 0 to 2 pi here, but sometimes you can modify the range on theta. And this r naught that's showing up in both of them kind of describes the length of the cardioid along its axis of symmetry. So if you were to calculate kind of how wide the specific heart-shaped curve is along the axis of symmetry, that's what r0 is going to be. So look at an example, maybe let r naught be 4, and let's say we want to be symmetric about the x-axis. So we're going to go up to the cosine version and make r naught equal to 4. Distribute, well, negative 4 over 2 happens to be negative 2. So if I distribute negative 2 to both terms, I'll end up with r of theta is 2 minus 2 cosine of theta. So how would I actually go about plotting something like this now that I've figured out what my function actually is? Well, it's going to be very similar to how we decided to plot parametric functions, and really how you've been plotting your entire life. You're going to choose a collection of values for theta specifically within its range, which in this case is 0 to 2 pi. And how do you choose those? You just kind of choose natural points that are going to be fairly easy to compute. So in our case, we're going to do multiples of pi over 6, since we actually know these on the unit circle, right? We know cosine at pi over 6, we know cosine at 3 pi over 6, which is the same as pi over 2, and so on. And so what do we actually have here? Well, I've got my multiples of pi over 6 in my table, so 0 pi over 6, 2 pi over 6, also known as pi over 3, 3 pi over 6, also known as pi over 2, 4 pi over 6, 5 pi over 6, 6 pi over 6, also known as pi, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6. And so where do the numbers for r come from? Like, for example, the first non-trivial one, 2 minus root 3. Well, I'm just going to plug this pi over 6 in for theta. And what do I get? Well, r of pi over 6 happens to be 2 minus 2 cosine pi over 6, and cosine of pi over 6 happens to be root 3 over 2. So this is 2 minus 2 times root 3 over 2, and the 2 cancels with the 2 in the denominator. I get 2 minus root 3. Similarly, I go through all of them. For example, at pi, I have r at pi is going to be 2 minus 2 cosine at pi, but cosine at pi happens to be -1, and so I end up with 2 plus 2. That's going to give me 4. That's how I got all those numbers for r. And now we just start to think about these. I'm going to reverse their order because when I write polar points down, I say r comma theta. So we're going to reverse the order of these. And I'm actually going to compute all of kind of my square root of 3's out as decimals. We end up with 0 comma 0 in polar, 0.27 pi over 6, 1 pi over 3, 2 pi over 2, 3, 2 pi over 3, 3.73, 5 pi over 6, 4 pi, 3.73, 7 pi over 6, 3, 4 pi over 3, 2, 3 pi over 2, 1, 5 pi over 3, and 0.27, 11 pi over 6. Now, let's actually think about, I've got the graph here of those points. Let's think about graphing them kind of independently of already seeing that down there. Let's put our plot in the middle of the screen. Give me maybe 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and let's think about this as a polar coordinate system. How would we plot something like 0, 0 on the polar coordinate system? Well, that's pretty easy because my radius is 0, so I have to stay at the origin. But maybe 0.27 pi over 6, I'm going to go out by 0.27 here, and then pi over 6 is about there. And so that's my 0.27 pi over 6. 1 pi over 3, well, 1 takes me up to here, but pi over 3 is going to take me up to here, so I'll have that point. 2 pi over 2, well, I'm going to go all the way up to 2, and then all the way up to pi over 2, that's going to be up here. 3, 2 pi over 3, I'm going to go all the way up to 3, which is over here, but then all the way around to 2 pi over 3, which is up here. And then 3.73, 5 pi over 6, well, 3.73 would be out there. 5 pi over 6 all the way over here. And then 4 comma pi, that's a rotation of pi, but I've moved 4 in the radial direction. 3.73, 7 pi over 6, well, that's really, here's still my 3.73, but now I'm coming around to 7 pi over 6, now I'm here. And without loss of generality, you should assume that this is symmetric, at least in this case. We're going to end up with kind of this collection of points. If I go ahead and connect the dots that I've drawn, right, my dots kind of get connected like the following. And this is going to be that heart shape. A little bit of a heart shape. Of course, it's on its side, right? Symmetric about the x-axis. Anyway, I've got all those points plotted here first and then connected with dots there as well. Another polar curve is the Archimedean spiral. This is as opposed to the logarithmic spiral, which we already saw in a previous example. This is going to be a spiral where the distance between adjacent arms remains constant. And the way that you can describe these in polar is with the function r of theta is some constant multiple of theta. Of course, that's kind of going to describe, that multiple is going to describe the distance between the arms. So for an example, let's make a equal to 1. It's kind of a very classic polar curve. It's, it looks like f of x equals x, but it definitely does not get graphed like f of x equals x. It's going to look substantially different than the f of x equals x graph. But we can plot this choosing a similar collection of values, but in this case I've let theta kind of go all the way out to infinity. And so we're going to have to make a natural choice of values of theta, even though we can't draw out to infinity. Maybe let's do multiples of pi over 2, because that'll be like nice quarter rotations every time we find a new value of r. So these are going to be the quarter rotations. So at least we can actually see the spiral occur. Well, the nice thing about the function r of theta is theta is, guess what? Here's theta, there's theta, but that's actually r, because r of theta is theta. Theta, r of theta, theta, r of theta, theta, r of theta. They're, of course, just the same number in every single case, but this does get a little bit complicated to plot, because you have to have some approximate value for pi, right? You need to know, so I've converted my pi's, at least in the radial directions, to their decimals, so that I can have an easier time plotting here. And so these are all like the numerical values of theta, but we're thinking about them as the radius r. And so if we plot each of these, and let's just plot them below and verify that 0, 0 is on there. There it is. Let's verify 1.57 pi over 2 is there. Well, here's 1.57 is about there. Pi over 2 is up. There you go. And maybe 3.14 in pi. That's, of course, right there. And if we go ahead and connect these dots in order, just like we connected the dots in order with parametric curves, we have to start here, make our way up here, make our way out here, make our way over here, make our way over there, make our way up here, over, down, over, up, over, down, and over. So there you can see the Archimedean spiral take shape, and I've of course got the very beautiful plot here as well. Now I do want to mention, kind of to finish everything out, it's pretty clear that polar curves kind of share a similarity to parametric curves. We're getting these plots in that xy plane or in the two-dimensional plane that do not pass the vertical line test, and yet we still have some notion of functions here. And so you might ask the question, is there a direct relationship between parametric and polar plots? And the answer is yes. Now, it turns out that this relationship is a lot easier in one direction than the other, and that direction is to start with a polar plot and end up with a parametric plot. To try to go in the reverse can only kind of sometimes be possible. There's a little bit more deep math behind that. So we're only going to focus on the one direction case, which is starting with a polar expression, ending up with a parametric expression. And this is going to make a lot of sense where it ends up, because if we take r being the radius, as well as theta being the angle, we know how to obtain an x and a y from our earlier transformations, right? X was always r cosine theta, y was always r sine theta. But what do we do in parametric world is we don't work with theta, we work with the new variable t, right? So t is our parametric variable. So all I've done is directly kind of replaced theta with t, that's why its bounds still reflect theta min and theta max, and then the x value of this parametric curve is just r cosine theta, but it's cosine t because that's the variable I'm using. And the y parametric curve is r sine t. So that's how you can convert almost immediately a polar equation into a parametric equation. And then if you want to use kind of all of your knowledge of parametric curves on the polar curves, you can. There's going to be some reasons to do this. Let me provide the reason for you. In the following example, something like r of theta is secant of theta. Maybe we're going to let theta go from minus pi over 2 to pi over 2. It's not quite clear how I might plot this. I mean, you could certainly grab some values in theta and connect the dots. But you would see if you just go through the work of converting it to parametric, then a lot of things simplify. So let's convert to parametric. And let's recall how we do that. Well, we just let x be r cosine of t, r being secant. We're going to replace theta with t in this case. So we're going to take secant times cosine, and secant times cosine, classically secant is 1 over cosine, right? It's just be 1 in the x direction. And then if we look at the y direction, y has always been defined as r sine of t, and so r of theta ends up being secant. We have secant t times sine t. Well, secant is still 1 over cosine. We're going to get tangent of t for the y direction. So now we're looking at values of x, which are constantly at 1, and values of y, which are equal to tangent. It's going to make your life a little bit easier to plot, because in fact, now we know every point has x equal 1, right? No matter how I'm plotting it, we're always going to have a constant value of 1. Actually, we can even think about the bounds as t goes to maybe negative pi over 2. What does tangent of t look like? Well, tangent's the graph that looks like this, and we have a nice vertical asymptote at negative pi over 2, where tangent goes down to minus infinity. We've got a vertical asymptote at pi over 2, where tangent goes up to positive infinity. And so the bounds in y are negative infinity to positive infinity. X is constantly at 1. There's exactly one plot between the y values of minus infinity and plus infinity and the x value 1. It is the vertical line, x equals 1, right? It goes all the way out to y is plus and minus infinity, and then you've got x equals 1 constantly. So that's how you would plot even the polar curve. That is the polar curve, r of theta is secant theta, but it's a lot easier to think about it as a parametric curve, x equals 1, and y happens to be tangent of t. We can also do the polar curve. R of theta is e to the minus theta. And in this case, we're going to let theta go from 0 to infinity. If we decide to convert to a parametric plot, we are going to write that the x value of our parametric plot is r times cosine, or in this case, because r was e to the minus theta, it's going to be e to the minus t, cosine of t. And then the y value is r sine theta, or r sine t, and the radius being e to the minus t times sine t. You may be able to recognize this from our previous section as the logarithmic spiral, right? So sometimes just doing that conversion says, oh, I've actually seen this curve before. I've seen the parametric curve before. And so we know it's a logarithmic spiral. I did go through the work of actually, calculating some points here, but because we've seen this as the logarithmic spiral before, we can almost immediately decide to plot it as the logarithmic spiral. So that's kind of the reason you may want to convert between polar and parametric, just to give yourself a better idea of how to plot some of these. Anyway, that's all I've got for you today. Finishing up this section, thinking about 2D curves. We're headed in the direction where we want to do some calculus with two-dimensional curves, but it turns out that the calculus is actually quite difficult, and so we're actually going to take a little bit of a detour and get even better at integration techniques. So there's going to be a vast collection of integration techniques that I know you're really excited about before we really try to get into calculus with some of these two-dimensional curves. Anyway, I'll see you then. Bye.